Ma'am, please start.
Yeah. Good afternoon and welcome you all in this 22nd lecture of SAMA-SPPU online lecture series uh, on atmospheric dynamics and its application to climate sciences. Today our distinguished speaker is Professor Sandeep Sukumaran sir from IIT Delhi, and his topic of talk is angular momentum, global angular momentum budget equation. I now invite Professor ABM retired Professor Ajit Tyagi sir for giving welcome address.
Thank you, Millie, and once again, welcome Professor Sukumaran for this lecture and thank him for sparing his valuable time. We are having a series of talks on atmospheric dynamics, and this is one the important talk which is going to be delivered today. As you know, the atmospheric dynamics plays a critical role in weather systems, and also the leading to the climate part of our studies. So this series is not only the basic dynamics but also its relationship with the weather and climate prediction and services. So this is a holistic lecture series, and we had been having lectures delivered by eminent meteorologists, academicians, and I'm really thankful to all of them. And in the same series today, we have got lecture on and I'm sure this will be immensely benefited. This all the participants, and as we always suggest that please feel free to ask question answers, and also make use of the YouTube availability post this talk also to clarify your any doubts. And also I request Professor to guide the students if anybody gets after the lecture also in touch with you. So thank you once again and welcome.
Thank you, sir. Thanks a lot. Now I invite Dr. Rohini to introduce our guest of honor, today's speaker, Dr. Sukumaran sir.
Thank you, Dr. Millie. I'll just share my screen. So yes, today's speaker, Professor Sandeep Sukumaran, is an associate professor at the Center for Atmospheric Sciences, IIT Delhi. His research aims to understand the dynamics of Indian summer monsoon as well as the monsoon's response to a warming climate. He uses climate models, data from coupled model intercomparison project, that is CMIP 5 and 6, observations and reanalysis to understand the changes in monsoon precipitation and circulation. He's also interested in the applications of AI/ML techniques in atmospheric science, and he has projects also related to all the above research ideas. He's also an associate faculty at Yardi School of Artificial Intelligence. He has more than 35 publications. He received his MSc in meteorology from Cochin University of Science and Technology in 2004, and he completed his PhD in 2009 from the Department of Physics and Meteorology at IIT Kharagpur. His research interests are the dynamics of Indian summer monsoon, the future changes in the Indian summer monsoon, and applications of deep learning in atmospheric sciences. He teaches different PG courses in IIT, such as Dynamics of the Atmosphere and Tropical Weather and Climate course, and he received Teaching Excellence Award for this particular course, that is Tropical Weather and Climate course, in 2021. He also has guided numerous PhD students and the master students, and still guiding. So we are happy that we have Professor Sukumaran here. Sir, please. Over to
Thank
you.
you, Rohini. Thank you, Rohini ma'am. And now I request Professor Sukumaran sir, please start your lecture, sir. You can share your screen.
Thank you. Thank you very much. Thank you, Dr. Millie, Dr. Rohini, and Dr. Diva Prakash. And also I thank Professor Somesh Das and AVM Professor Tyagi sir for inviting me for this lecture series. So I again thank all of you for the kind introduction. and also I welcome all the participants. So I will now start my lecture, and the participants can ask questions. Feel free to ask any question at the end of the lecture. And also, as AVM Professor Taggi told, I will be happy to receive any questions from the students even after the lecture. Anytime you can contact me through email. I would be happy to answer your questions. So let me share my presentation.
Yes, sir, it is visible.
Yeah. Okay, so today's topic of the lecture, angular momentum budget and transport mechanisms. So I'll briefly outline the objectives of this lecture. First of all, I would like you to understand the concept of angular momentum in the atmosphere, and we will derive and interpret the global angular momentum budget equation and zonal angular momentum, and we will also analyze the role of or we will understand the role of surface friction and orography in the angular momentum budget. So I will start from the very basic, what very basic question of what is angular momentum. So I hope that all of you know this. The angular momentum is a measure of an object's rotational motion, and it is analogous to the linear momentum, which is mass multiplied by velocity of an object. But here, this is this is angular momentum is for the rotational motion of an object. So both linear and angular momentum are conserved quantities for a closed system when an external force is not applied. So this is very important. The conserved quantities are very useful for our understanding of atmospheric dynamics. So we will come to that. So I will also I also like you to have a look at this picture. This is a very broad view of atmospheric circulation. So you can see that in the tropics, it is mostly easterly winds, which means the winds are mostly flowing from east to west direction. While in the extratropical regions, it is in the opposite direction. It is mostly westerlies. So you try to have this picture in your memory. So this is very important in understanding the angular momentum budget of the atmosphere. So, we will get an answer. Why do we have this kind of a wind pattern? In the tropics, we have easterly winds, and in the extratropics, we have westerly winds. So there is a reason for that. We can explain that using what we are going to learn today. So I told that the angular momentum deals with the rotation of an object. Here, we all know that the Earth is rotating on its axis from west to east. So like this. So Earth has an angular momentum. And atmosphere is also rotating along with the Earth, and also atmosphere has its own motion. I just showed the wind patterns. So atmosphere also has an angular momentum. So together, the absolute angular momentum of the climate system, which includes the Earth and the atmosphere, the total angular momentum should be conserved. So otherwise, what will happen is that the rate of rotation of Earth may change. So in that case, we won't get equal duration for our day. It won't be 24 hours always if the rotation of Earth keeps on changing. That is not happening, although there is I will later explain a little bit a smaller variation in the Earth's rotation that we don't usually know, but precise measurements tell us that there are fluctuations in the rotation. So I see there are some raised hands. I think I can take questions at the end of the lecture.
Yeah, sir. The questions will be at the end of the lecture only.
Yeah.
Yeah.
So, okay, thank you. So if, as I said, if Earth is gaining angular momentum, then it should accelerate, or if it is losing angular momentum, it should decelerate. So in either way, there will be a change in the duration of the day, but we don't experience any such thing, except for some small changes that I will explain later. So this means that the angular momentum, the absolute angular momentum of the Earth atmosphere system is conserved. So we will see how this is conserved in a short while. So some of the equations for this conservation, and you need to understand this basic I mean, how we are going to derive this. So because we are dealing with a spherical Earth, we will use spherical coordinate system. So here we I think again that this you must have already learned that the angular momentum per unit mass is absolute velocity multiplied by the perpendicular distance from the axis of rotation. So here, this is, you can consider this vertical line as the axis of rotation. Here, omega is capital omega indicates the angular velocity of Earth, which is simply 2 pi radians divided by 24 hours. You will get like 7.26 into 10 to the power minus 5 per second. So here r is not the radius of Earth, but it is the perpendicular distance from the surface of Earth to the axis of rotation. So this is something you need to be mindful about. Don't confuse this with. So here we indicate A, use the small letter A for the radius of Earth. So exactly at equator, both these will be the same r is equal to A, or the perpendicular distance from the axis of rotation and the radius of Earth will be the same at the equator. But as you go away from equator, this changes. You can see that at equator R, this is the R and this is also the radius. But at this is hypothetically, let us assume that this is 30° north. You can see that the perpendicular distance from the axis of Earth is smaller compared to that from the equator. As you go further north, it will further decrease. So as you go towards pole, it will decrease, and exactly at the pole, it will be 0. So then obviously we can say that R is equal to A, which is the radius of Earth multiplied by cos phi. Here phi is this angle, which is also the latitude in the perpendicular distance from the axis of Earth to the rotational axis of Earth to the surface at that particular location. So the angular momentum is absolute vorticity, which let us say this is we can denote that using V. So absolute velocity and the angular velocity we can relate using this equation. It is absolute velocity is equal to angular velocity multiplied by this distance, perpendicular distance from the rotational axis of Earth. So V is equal to R omega. So we can say that angular momentum, which is denoted with capital M. So angular momentum, we can say that it is equal to omega R square. So 1 R, it came from, we converted this absolute velocity. We defined it using the angular velocity and the distance from the axis R, and then again you need to multiply that with R, because absolute velocity into the perpendicular distance from the axis of rotation, which is the angular momentum. So R omega into R, it will give you omega R squared. So this is the angular momentum of the let us say this is the angular momentum of the Earth. So now I stated that the absolute angular momentum of the Earth atmosphere system should be conserved. Otherwise, there will be an acceleration or deceleration. But this is valid for the whole Earth. What will happen at the local level, or what will happen to an air parcel, say. So let us assume that an air parcel which is originally sitting at the equator is moving poleward. Let's say it is moving towards the subtropical region. So what will happen to that air parcel if that air parcel, let us assume for the time being that that air parcel conserves its angular momentum. So now this air parcel is moving from equator, where R is equal to A, to, let us say it moves to 30° north, where R decreased to some other value, which is A cos phi. So then how does it conserve its angular momentum if it want to retain the its original angular momentum at the equator? So let's see how this is happening. So before going to that angular momentum, one moment. So there was a problem with my network, so I'm coming back. Yeah. Okay, so I was talking about the total angular momentum of the atmosphere and Earth, but we can separate that. For atmosphere and Earth, we will define angular momentum separately, and total angular momentum we can take it as a sum of these two. So this is important to understand the what will happen to the atmosphere, or how the angular momentum exchange is happening between atmosphere and Earth. So this omega r square, this is the angular momentum. Here we define it as angular momentum per unit mass. So this is the angular momentum per unit mass for the Earth. So we can call it omega angular momentum. So you in textbooks you see different types of notation. So you can see sometimes omega. So it denotes the angular momentum of the Earth. And let us assume that the air parcel at the equator, originally it has a velocity of u. So then its angular momentum will be that velocity multiplied by r. So it will be ur. So total angular momentum of this system will be omega r square plus ur. So now, if we replace r with a cos phi, we can write it as m is equal to omega a cos phi plus u. This is the air parcel's initial velocity multiplied by a cos phi. So this atmosphere's angular momentum, or this air parcel's angular momentum, we can call it as a relative angular momentum. In textbooks, you can see that it is denoted using mr. It is simply ua cos phi, and the Earth's angular momentum
Some network issue is there, I think.
Network issue?
Yeah,
Yes, sir.
I also can't see. Yeah.
Yeah, he's not in the meeting. He will rejoin, I think.
Disconnected.
Mm-hmm.
I'm back now.
Yeah, no.
I'm
Just
sure of the
say it again on the screen.
network. Hope that this will work. So yeah, I hope that you can hear me.
Yeah. We can hear you,
Yeah.
sir. You share your screen. Yeah.
Yeah, let me share again. Can you see
Yeah,
my?
yes, yes, sir.
Okay,
Yes, sir. It is
okay.
coming now.
Okay. So, right. So the angular momentum for a closed system should be conserved. So we will discuss whether this air parcel is a closed system or not later. Let us assume that it conserves the angular momentum. So let us see how this is happening. So the angular momentum at equator, let us call it omega r square at equator, should be equal to omega r square at 30 degrees north if this is to be conserved, or let's say that the total angular momentum, so m is equal to omega a cos phi plus u into a cos phi. So this is the total angular momentum of the Earth plus that air parcel. So that should be conserved while it is moving. So let us try to find the angular momentum, how this is being conserved as the air parcel moves forward. So here, if you see omega, the omega is the angular velocity of Earth. It is a constant. It does not vary with latitude. So it is everywhere it is 2 pi radians divided by the time taken to complete one rotation. So A is the radius of Earth. It is also constant, and B change when the air parcel moves from equator to poleward. So the phi is variable. It changes. So then in this, if you see this equation, if you want to conserve the absolute angular momentum, then there is only one way to do that. So these are constants, and phi is something that varies with the air parcel moving, and then there is only one variable that is left, which is u. So it is the zonal velocity of the air parcel. So if the air parcel, let us say that it was stationary, it does not have any zonal velocity at the equator, which means u is equal to 0. In that case, what will be the velocity? It needs to adjust its zonal velocity to conserve the angular momentum at different latitude. So basically it needs to attain a non-zero value. It should be greater than 0 if its original velocity was 0, or basically u should increase its zonal velocity should increase as it goes north to conserve the angular momentum. So it is because the distance from the axis of rotation will decrease as you go north. So phi is equal to 0 at equator, which means omega a cos phi will have a certain value. And as you go further north, let's say at 30 degrees north, cos 30, omega a cos 30 will be definitely less than its value at equator. So it means the other term should increase to compensate for that reduction in the horizontal distance reduction coming from the effect of that horizontal distance from the axis of rotation, the vertical distance from the axis of rotation to the surface. So it will be compensated by an increase in u. So what does it mean for an air parcel starting with u is equal to 0 or 0 zonal velocity. It does not have any eastward or westward movement at initially. It's purely moving in the northward direction. So we can basically apply this constraint, and we can derive an expression for zonal velocity by conserving angular momentum. So this is an angular momentum conserving velocity u phi. We will get if we do some rearrangements, we get this expression u phi is equal to omega a sine square phi divided by cos phi. So using this expression, we can find the angular momentum conserving velocity of an air parcel starting from equator moving poleward. So I am since we are in the northern hemisphere, it is convenient for us to talk about the movement in the northern hemisphere, but you should understand that the same thing will happen in the southern hemisphere also if it moves equator to poleward in the southward direction. So let us now, this is a very convenient relationship. We know the values of omega and a. So these are constants. The radius of Earth and the angular velocity of Earth, these are known. And phi is the latitude at which we need to know the value of u. So if we simply put all the values in this equation, we will get that at 20 degrees north. Let us say that phi, the air parcel moved from equator to 20 degrees north latitude, then we see that it should attain a zonal velocity of 56 meters per second to conserve the angular momentum. And if it moves to phi is equal to or latitude 30 degrees north latitude, then it should attain a zonal velocity of 127 meters per second. So is this happening in real atmospheres? We can look at the velocity that is observed in the subtropical jet stream. So in the jet stream, something that is analogous to what we have discussed is happening here. Near the equator, we see a vertical motion in the atmosphere. It is mostly convective transport that is happening in close to the equator, which means the air parcel is moving upward direction, and then it diverges to either hemisphere. It moves poleward from that position. So this is analogous to what we have discussed about the air parcel's movement. So the velocity that we have seen in the subtropical jet stream is about 45 to 50 meters per second, which is much less than the value that we got at 30 degrees north, which is where we see the core of the jet. So it is much smaller than this 127 meters per second. So what should be happening here? Obviously, there is no conservation of angular momentum for that air parcel. So then it should exchange angular momentum with something else. So that we will see in a short while. So, but this is at the same time this conservation of angular momentum it is a powerful constraint to understand the atmospheric circulation. So we will see what is happening if it is not absolutely conserved for that air parcel. What are the processes happening there that we will see in a moment. So this is a figure that shows the distribution, the vertical, this is basically the vertical and zonal distribution of angular momentum here. The unit of angular momentum is kilogram meter square per second square. And these are the zonal average velocities. So basically you can see the jet streams, subtropical jet streams on either side here. So now we will derive the angular momentum balance to understand what is happening. It is not being conserved in a very simple way, or it is not, the angular momentum is not conserved at each individual points of Earth, or each individual air parcel is not conserving the angular momentum, which means that there is an exchange of angular momentum that is happening between the atmosphere and Earth, and also from in the atmosphere itself, the angular momentum is being transported from one place to other. So how is this happening? So simply mathematically we can say that if angular momentum is not conserved, or a smaller region, we can say that the dm by dt, or the time rate of change of angular momentum, is not zero, or m is not constant. And it is because it is not a closed system. So initially I mentioned that the angular momentum of a closed system is conserved. So the angular momentum is not conserved when an external torque is applied to the object. So we will see what are the torques that are acting here in our Earth atmosphere system. So basically there are two ways of exerting torque on atmosphere. One is by the zonal pressure gradient. So mostly this zonal pressure, means in the east-west direction. So I hope that most of you have the background in meteorology and understand the conventional terminology. So if we have zonal east-west pressure gradient, so that will act exert a torque on the atmosphere, or a force on the atmosphere. And second is surface friction. When it comes to the pressure gradient in the east-west direction, it is mostly due to the effects of the mountains. If a mountain orography is there, then it blocks the flow of the air or the winds, and then its windward side and leeward side will have different pressures, and as a result there is a torque exerted on the atmosphere. And surface friction, of course, it applies a torque or a force on the atmosphere. So these can act as these can cause basically the changes in the atmospheric angular momentum. There is one more thing that we usually neglect. It is what we call tidal and extraterrestrial torques. So tidal means it is the lunar or due to the gravitational effect of moon and other planets and extraterrestrial gravitational effects. Basically, it can change Earth's rotation in a very small way. It acts as a torque, but it has a very negligible effect unless you look at it in the time scale of a millennium, or a very large time scale of the order of a century or so. This is very small, and we can neglect it, and we can say that the atmosphere Earth system is a conserved. Its angular momentum is conserved, but within that closed system, there is a lot of exchanges that are happening. That is what we are going to see now. So now, if this is not zero, the rate of change of angular momentum is not zero, then it should balance with some other forces. So we have already seen that there are two forces that are important. One is the pressure torque due to the effect of mountain. We denote it using minus dou p by dou lambda. Here lambda is because we use the spherical coordinate system. So this is the longitudinal direction. So the derivative. So there is an east-west pressure gradient due to the effect of the mountains. And second is the frictional torque, which is expressed here, rho f lambda r cos phi. So this term indicates the frictional torque. And then there are tidal and other etc. silk torque. For the completion of this equation, it is shown here, but from here onwards, we will drop this term. We consider this as a very, very negligible term, and we consider only two terms on the first and second terms on the right hand side. And here I assume that you know the total derivative. So here d by dt is basically, this is local rate of change, and then this is the advection. So we dropped this term tidal and other extraterrestrial torque, and then we can rewrite our equation this way. Here rho is the density of the atmosphere. So rho dm by dt is equal to minus dou p by dou lambda plus rho f lambda r cos phi. So now, if we consider if we consider a volume, a unit volume of the atmosphere, then we can further modify this equation. So we basically time rate of change the advection terms be separate. And we consider the atmosphere compared to the Earth's radius, the Z, which is the thickness of the atmosphere, it is much less. So for practical purposes, we can consider or we can neglect that thickness effect of the atmosphere. So here now, this is the first term on right hand side. This is coming from the advection term. So this is basically divergence. This indicates the divergence of the angular momentum. So suppose, what does it mean? Suppose you are in the tropical region. Let's say we assume that there is a wall around it. There is a boundary at 30 degrees north. Okay, so then this term indicate, basically tell this term basically tell us about the exchange of the angular momentum happening through that boundary. It is, we call it the transport of angular momentum. So we have seen that and when from the tropics there is a convection, and then air parcels move northward. So it is moving in the polar direction. So which means that these air parcels are taking angular momentum from tropics, and it is moving to the in the polar direction. So some place will lose this, or there is a decrease in the angular momentum over, let's say, tropics, and then if it moves to the extratropical region, then that region will get angular moment. It will increase. So if we sum it, so then if we integrate it over the whole Earth, this term will vanish, because it is just transport term. Angular momentum is being transported from one place to another place. So from where it is transported, it will get decrease, and from where it receives, that place will get there is an increase in angular momentum. So if you add these two, it will become 0. So when we integrate it over the whole Earth, it will vanish. But for our purpose, this is very important. This term explains the transport or movement of angular momentum from one place to other. And then this term, the second term, is the pressure torque, due to it is also called mountain torque, minus dou p by dou lambda. And then this third term is the friction. So if we integrate, as I said, if we integrate it for the whole atmosphere across the globe, then obviously this term the first term will vanish, and then we will have only two terms on the right hand side. So let us denote the first term with P, which is the pressure torque, and the second is the frictional term. So here you see that we can write F, which is the friction, which I hope that you have learned the derivation of the momentum equations. So where you must have already seen this, the friction, we can express it as minus 1 by rho del dot tau. So tau is basically surface stress, or basically when wind flows at the surface of Earth, there is a frictional effect. This indicates that frictional effect, or we call it surface stress. So this term r square cos square phi d phi r d phi. So you can also, this r also you can bring here, it can be written as r cube. So this is basically the differential area element on a spherical Earth. So this term, obviously this is a frictional term, it acts along the surface. So this is a surface integral, and other two are volume integrals. So this equation basically tells us about the total the angular momentum balance of Earth atmosphere system. So we will see how these terms on the right hand side can be calculated. So first we will look at the term due to the friction, the mountain torque. So we can let us assume that there are say a number of mountain ranges. So this picture, which is taken from the textbook Physics of Climate by Picciotto and Wood. This is so here you are basically looking from the top of North Pole downwards. So this is the North Pole, and it is very idealized visualization. So this is one mountain, and this is another mountain. So you can and the circulation is indicated here this way, these arrows. So this is the windward side, and this is the leeward side. PW indicates the pressure on this side, the windward side, and PE indicates the pressure on the other side. It's eastern side, or the leeward side of the mountain. So the difference in pressure between east and west of the mountain will give that pressure torque to the atmosphere. So now what we are doing is we sum it over all the mountain ranges in a latitudinal circle, in a particular latitude. So there are n number of mountain ranges in this latitudinal circle. So you sum these pressure torque across all those mountain ranges. So it will give us the total pressure torque exerted by these mountains on the atmosphere. Obviously, if there were no mountains, if you assume the Earth as a very smooth, nice sphere, then the mountain torque will naturally become zero. And the second, frictional torque basically adds angular momentum to the atmosphere. The mountain torque reduces. I mean, these two torques will help in the exchange of angular momentum between Earth, the solid Earth, and the atmosphere. So the frictional torque, for example, the frictional torque will add angular momentum to the atmosphere in the case of easterly wind. So if in the picture that I have shown in the first slide, you may be remembering that in the tropical region we have easterly winds, which means the winds are flowing from east to west. So that will add, it is opposite to the rotation of the Earth. So then that will add angular momentum to the atmosphere. So the solid Earth will lose some angular momentum, and the same amount of angular momentum will be gained by the atmosphere at that location due to the easterly winds. And similarly, the westerly winds will take away angular momentum from the atmosphere and transfer it to the solid Earth. So in the extratropics, you have seen that the winds are westerly, flowing from west to east. So it is in the direction of rotation of Earth, and these winds add angular momentum to the Earth. And atmosphere loses there. So basically, also the upward motion adds angular momentum to the atmosphere, and sinking motion removes angular momentum from the atmosphere. So then we understand this basically explains why we have easterly winds in the tropics and westerly winds in the extratropics. The angular momentum gained by the atmosphere in the tropics will be lost in the extratropical region. So the net effect is the conservation of angular momentum in the Earth atmosphere system. But if you look at the tropics alone, then there is no such absolute conservation of angular momentum. If you look at extratropics alone, there is no such conservation. But when you take the planet Earth as a whole and the atmosphere that envelops it as a whole, there is a conservation of angular momentum. But from tropics to extratropics, there is a transport of angular momentum. The excess angular momentum that atmosphere gains from the Earth is being transported to the extratropical region. So how is that happening? So basically, the transport term in the equation that I have shown explained previously, it facilitates the transport of angular momentum from tropics to in the poleward direction. So it is manifested basically through a few processes. One is the zonally averaged these overturning circulation in the tropics. You know, the Hartley cells and in the extratropics there are the Ferrel cells are there. So these Hartley cells helps in transporting angular momentum from tropics to extratropics. And more than that, there are what we call transient eddies. So these are mostly the cyclonic storms, the extratropical cyclones. These are transient eddies. Our western disturbances are also a class of these type of eddies. So these here you can see the trajectory of these eddies. There are several such systems form, especially these are most prominent in the winter season. I will soon come to the seasonality of the angular momentum. So in the winter season, we see the jets, the subtropical jets are stronger in the winter season. And if you remember, we have seen that the angular momentum conserving velocity is not observed in these subtropical jets. So why is this happening? It is because these as the velocity increases, the frictional effect with the surface will also increase, and the jet becomes so unstable that it has to break down into the eddies. So basically these eddies, you can see that a lot of these storms, these eddies are forming at the poleward edge of the jets. So these eddies play a bigger role in transporting angular momentum to the extratropical region. So here again, this figure shows the angular momentum transport by this is by all types of motion, like Hartley cell and eddies, and there are also stationary eddies. These are basically the semi-permanent high pressure cells, and that kind of stationary eddies are also there. So but they contribute in a very small way to the transport of angular momentum. Here you can see this is the angular momentum transport by the transient eddies. These are the cyclonic storms. So here, if you see the total, large fraction of that is contributed by the transient eddies. And then the mean meridional circulation, like Hartley cell and Ferrel cell, these also contribute. These play a secondary role to that of the transient eddies in transporting the angular momentum to the extratropical regions. So I told that in the winter season we see most of these eddies. So it is because in the winter hemisphere we see increased angular momentum, and also the Hartley cell is also stronger in the winter hemisphere. Basically, Hartley cell tries to transport heat from summer hemisphere to the winter hemisphere. So as a result, there should be a net transport from summer hemisphere to winter hemisphere. So you can see its reflection in the angular momentum also. So this is again vertical cross-section of angular momentum as a function of latitude and height, you can see. And the top is the annual mean, which is almost symmetrical between about equator. Some asymmetry, you can see it is because of the asymmetrical distribution of land mass between the northern and southern hemispheres. And in the this is the winter DJF, our north hemispheric winter. You can see this angular momentum transport is stronger in the winter, and this is June, July, August. So it is now more stronger in the southern hemisphere. That is their winter. So we started the discussion with the lecture with the mentioning of the rotation rate of Earth, and I told that if the angular momentum is not conserved, then the Earth can either accelerate or decelerate depending on whether it gains angular momentum or loses angular momentum. But we see that Earth as a whole conserves angular momentum, but there is another catch. This is not at any particular instant in time. So when we average the angular momentum budget over sufficiently large time, let's say that several years, you can take a decade and average it, then you will see that okay, it is conserved, but from one instant of time it is not conserved again. So it is then reflected in slight changes in the length of the day. So the order of magnitude of the fluctuation in angular momentum of the atmosphere is found to be about 5 into 10 to the power 25 kilogram meter square per second, which is much smaller than the total angular momentum of the globe, which is about 8 orders of magnitude larger. So it means that this fluctuation in angular momentum of the atmosphere is not going to change the rotation of Earth in a substantial way. But if we make very precise measurements, then we will see that there is a small fluctuation in the rate of rotation of Earth, and as a result, the length of the day. So there is an empirical formula that relates the change in the length of day and change in the angular momentum of the atmosphere. So delta MR indicates the change in the angular momentum of the atmosphere. So if we multiply that with 0.168, approximately, we will get the change in the length of the day. So for a typical value of 5 into 10 to the power of 25 kilograms per second, we get a change in length of day of about 0.8 millisecond. So this is millisecond basically. So which is very small. We do not feel about that change, but it is happening. So this graph basically shows this is a time series of length of day calculations, again taken from the textbook Pixoto and Wood. Here you can see that the length of the day is actually fluctuating from year to year. So we can also see there are people who studied and related this to natural phenomena like ENSO. So for example, during El Nino years, we found that the angular momentum transport increases and from the tropics, and as a result, the length of the day also consequently increases. So the most of these fluctuations are due to these kind of natural phenomena. So there are some recent studies that looked at the effect of climate change also, and they also suggest that there are some intensification of jets, and that can increase the atmospheric angular momentum. But these are all contributing in a very tiny change in the length of the day. So with that, I finish, and I'm ready to take questions.
Thank you, sir. Thanks a lot for giving wonderful lecture. And now there is time for photo session. So I will request Dr. Deeprakash to click the photo. And before that, all the panelists, please switch on your video. Dr. Tyagi, sir. Yeah, now all are there. So Dr. Deeprakash, please click.
Vani ma'am, ये
Yes.
I think आपका hand आ रहा है कोई proper
Oh.
photo नहीं आ रहा
Okay, okay.
हाँ अभी done ma'am, done.
Okay.
Thank you.
Okay. Thank you. And now I invite Dr. Deeprakash for moderating question and session.
Yes, miss. Thank you so much, ma'am, and thank you, Sandeep sir, for delivering very great lecture. So there are some questions, and now I am taking one question, which is asked by Preeti. Does angular momentum transfer maximum around mountain ranges during ENSO period across the globe? Am I audible?
Yes, yes.
Yeah.
So is that it looks like a statement. I mean, is that a question or?
Yeah, question is, does angular
Yeah.
momentum transfer
Yes.
maximum around mountain ranges?
It's not just mountain ranges. So the mountain ranges, I mean, it does not have, direct relation with ENSO. The question is on ENSO and
Yes, sir.
angular
Yes, sir.
momentum transfer, right? So
Yeah.
what happens is that during ENSO, we see a change in the convection pattern and also change in the wind patterns in the tropical region, right? So that actually increases the exchange of angular momentum from earth to atmosphere in the tropical region, and this will be transported to the extratropical region, so which will be manifested by change in the wind velocities there, and obviously then it interacts with the mountains. There is a change in the torque. So the mountain torque acts as a decelerating force. So yes, during it's not the mountain is there, it is always there, it is a constant thing, but it is because of the change in the wind speed in response to the change in the angular momentum exchange between earth and atmosphere during ENSO. That is why we see change in the angular momentum exchange elsewhere, like during interaction with the mountains. I hope that it is clear.
And so there is one request from one participant. Please share PPT with us. So this is and there is one another question. Can be used momentum budget and energy budget to explain general circulation?
Definitely. So the momentum budget is this is actually important for explaining the atmospheric general circulation. There are many studies. For example, you can actually since this is just 45 to 1 hour, 45 minutes lecture, so I cannot actually bring all the information here. So if you are more interested, you can actually follow this textbook. Pixoto and Root is actually, it gives a very nice treatment of angular momentum budget and the general circulation. So I recommend those who are interested to read that textbook. And yes, of course, I think I shared a version of the PPT. I mean, I will share the updated version of PPT with the organizers, and then you can forward it to the students. Yes, absolutely fine. You're muted, Dr. Divya Prakash.
Please unmute.
Yeah,
Dr.
please.
Divya, you're muted.
Sorry.
Yeah.
Sorry. So there is one question from Anjana. Can you please explain about the formation of transient eddies once more?
Okay, so the transient eddies mostly form at the around the same location at the jet streams. The if you see the subtropical jet stream, that is the place where you see many of these transient eddies forming. So why it is forming there? Because there is a huge shear in the wind shear, because at the core of the jet you see maximum wind speed, and as you come closer to the surface of Earth, the atmosphere experiences more and more friction, and then that the wind speed reduces. So as a result, you see there is a strong wind shear in the regions of jets. So what happens is that this shear is basically, it will lead to a baroclinic instability, and it destabilizes the jet stream, and it transforms into these kind of cyclonic eddies. So again, I think it may need another lecture to actually explain all these processes in detailed way. But yes, there are many standard textbooks that explain this. I hope that, I mean, this answers the question.
Thank you, sir. So now there is no more question.
Thank you, Dr. Tiprakash. And
Thank you.
yeah, now Munal is not present, so I will give the formal vote of thanks. Just wait. Yeah. On behalf of the organizing committee of weekly online lecture series on atmospheric dynamics and its application to climate sciences, I would like to thank ABM retired Professor Ajit Tyagi sir, President SAMA, for giving welcome address and brief information about this lecture. My deepest appreciation goes to our speaker of the day, Professor Sandeep Sukumaran sir from IIT Delhi, for delivering very informative lecture on angular momentum, global angular momentum budget. I also thank to Dr. Rohini Bhavar, SPPU Pune, the program convener, for introducing today's speaker. My sincere thanks goes to Dr. Deep Prakash for moderating question and answer session. I express my heartfelt thanks to all the panelists and participants who joined us from across the globe. Last but not the least, I want to thank team members of Savitribai Phule Pune University for their support in organization of this lecture. Thanks to you all. And now I request Professor Someshwar sir to please say a few words for this lecture.
Sir, do you want me to give the statistics before we?
Oh, yeah, please. Yeah, please.
Yeah, okay. So 94 participants have recorded their attendance, out of which 84 participants have rated as excellent or very good.
Yeah, very good. So, well, thank you very much, Dr. Mili. We thank back to Professor Sandeep Sukumaran for the interesting lecture that he has delivered in such a complicated topic on global angular momentum budget, which is not easy to comprehend in just one lecture. A lot of live examples of the impact of the angular momentum budget of the atmosphere, its transport, from one region to another region, and also the development of the atmospheric weather systems because of the transport of the global angular momentum. Of course, Professor Sukumaran has already given some examples, but participants will have to read if they are interested to know more live examples of the momentum budget. I mean, you can imagine, for example, if you just see the weather systems like, say, for example, tropical cyclone or say tornado. See that the radius of curvature in a tornado is much smaller than the radius of the maximum wind of the cyclone. And so you can imagine that the wind speeds are much furious, much stronger. The angular momentum is much higher in case of the uh, systems where the radius of curvature is smaller. So I mean, they're just small live examples of the impact of the angular momentum. It is not just the Earth's rotation only, but also the angular momentum of the atmosphere, the mass of the air mass which is rotating around it. So a lot of interesting applications, the angular momentum of the globe. And Professor Sukumaran has tried to summarize all the important things in just one lecture. With this, we could request him for more lectures, but we have already exceeded almost 6 months of this lecture series. Generally, we conduct for 4 months, but it has taken almost like 6 months. Satellite meteorology, we conducted for 5 months, and similarly, radar meteorology also we conducted for about 5 months. But this lecture is exceeding 6 months. So, probably we cannot go much in detail, but certainly, yes, you can read more, and if you are interested, you can ask questions. We can definitely help you. As Professor Sukumaran said that he will share it PowerPoint and will also share it with you. And if you can provide a brief summary of the lecture, Dr. Sukumaran, that will be also easy for the participants to understand. The participants have got a they have registered for 50 plus countries. 50 plus countries, not only that is beyond South Asia. Many of them are members of the non countries like from South Africa, from Indonesia, even some from Europe, etc. So many people from these developing countries, they have registered who have absolutely no background of meteorology. Some of them are just like a freelance worker on climate change. And so just by hearing that, we're going to have a lecture series on the applications of atmospheric dynamics on climate science. So many of them have registered for it. For them, it will be quite difficult. For some of them, it will be quite difficult. Some of them are, of course, MSc students. Some are doing PhDs. Some are even doing like young scientists are also there. So, in a wide range of professionals who have registered for this course. And we have said in the beginning that we had for this lecture series, we didn't conduct a midterm test, which we conducted for the last lecture series, but we still have the online test at the end of the lecture. And as I said in the beginning, I think only 3 more lectures are left. This is the 22nd lecture. 23rd and 24th lecture will be from Professor Ananda Karipur from Pune University, and the last lecture will be from Professor C.A. Babu of the Cochin University of Science and Technology. He had delivered 2 lectures earlier, and this will be his last lecture. And after that, there will be, of course, the online test. And based upon your attendance, because we announced at the beginning that those who have more than 75% of attendance, they will also get an attendance certificate. And the remaining participant will get just a participation certificate. And those who score good grades in the final test, online test, they will get a grade certificate also, like excellent or outstanding, depending on your score. It's more than 85% or more than 80% and things like that. So please be attentive, and if you have missed some of the lectures, or if you could not understand some of the lectures, please go to the YouTube. All the lectures, past lectures of the all the lecture series are already archived on the YouTube channel of SAMA. So you can watch as many times as you want on the YouTube, all these lectures, and make your concept clear. And if you have still questions left, then you are always welcome to send an email to us, all the participants, and then we'll definitely try to answer it. But be prepared well, and certainly we shall have, after 3 lectures, a final online test examination. We shall announce it properly before that. So that's it from, I think, my side. Thank you so much once again, Professor Sukumaran, and our entire team, including Professor Milik Ghosh, Dr. Rohini, Divya Prakash, and of course the President of SAMA, AVM, retired Professor Dr. Mittal. Thank you, sir. Thank you so much.
Thank you, sir, for your nice words and brief information about the exams. And now, with permission of ABM retired Professor Ajit Tyagi, sir, shall I end the session?
Thank you, Millie, and thank you all of you for conducting this lecture efficiently. And thanks to Sukumaran for delivering a very, very insightful lecture. And I'm sure the students, participants have benefited. And as requested earlier also, that participants should make use of the recorded lecture PowerPoint presentation, and if need be, could contact Professor Sukumaran for further updates and verifications. Thank you.
Thank you.